So the daily problem is possible bipartition, which says we want to split a group of n people labeled 1 to n into two groups of any size. Some of them dislike each other and they can't be grouped together. So dislikes at I contains A and B, and then A and B can't be in the same group. Is it possible to split everybody into two groups? Return true or false. So it's sort of another kind of graph problem. And it's also a problem where truly you can kind of just try to split everybody into two groups. There's a lot of questions that are like, return the number of possible ways to do blank. And then they often say the number may be very large, so return it modulo 10 to the 9th plus 7. And in those, you can't just iterate through every possibility. But here, we really can just try and split everybody into two groups. And if we ever run into an error, then we immediately can return 0. And if we don't run into an error, then all we really have to do is iterate through every person. And actually, that's the first thing that we're going to do is we can kind of think of dislikes. This might as well be called edges. But instead of connecting two nodes, it's kind of a reversed connection between two nodes. And just like given edges in the previous few daily problems, we can just turn this into an adjacency list. So we'll say ADJ equals, we could say default dict list, which kind of gives us a list of lists, but that involves hashing, and I think that takes a little bit more time than saying something like this. Except we want it to be n plus 1 because this is 1 indexed instead of 0 indexed. So there is an nth node instead of it going to up to n minus 1. Which means here the 0th index will never be used because there's no node at 0. That'll just always be an empty list, but that's fine. I think that's still faster than having to hash numbers into themselves with some sort of universal hashing algorithm. Anyway, and then we just say for A, B in dislikes, ADJ at A dot add B. We want to append ADJ at B dot append A. And then once we have this adjacency list, we can kind of start to think about this as a graph. And the way that I'm thinking about this is, let's say we know that we have one set, one group, and node 1 is in that group. If node has any connections, all of those connections have to be in group 2. They can't be in the same group as this node that they're connected to that's in group 1. And then if any of those nodes in group 2 are connected to, say, each other, or another node that we already know is in group 2, or even if node 1 was connected to a node that was already in its own group, we can immediately return 0. So the way that I'm thinking about this is that we perform a breadth-first search, and we're kind of, it's almost like a level order search, where we're saying there's this node, there's all the nodes that it's connected to, they have to be in a different set. There's all the nodes that those are connected to, those have to be in the first set, and then the nodes connected to that have to be in a different set, and so on. So it's sort of this concentric striped target pattern that the graph has to make. And if it doesn't make that, we return 0. If it does make that, we return 1. So I'll make two sets to represent each group. We'll just say first, second equals set, set. And then we'll use a Q, and we'll say Q equals DQ. And if you think about it, it doesn't matter what node we start with. We can start with whatever. Because at the end of the day, if it's possible, then the two groups are interchangeable. You could have all the nodes that are in group 1 be in group 2, and all the nodes that are in group 2 be in group 1. As long as they're distinct, you could just swap back and forth between them. So I guess what I'm trying to say is, let's say you have one group that's like 1, 2, 3, and then your second group is like 4, 5, 6. You could say, this is the first group, this is the second group. Or you could say, this is the first group and that's the second group. And it doesn't really matter. And that seems kind of obvious when it's stated like that, but the more deeply you understand that transitive nature, the more free you are to do things like just say, all right, start with node 1. I don't even care what group it's in. It could be in first, it could be second, who cares? So then let's build this out by making a breadth first search. So we'll say while q, a equals q dot pop. We'll keep their syntax in this question. And then for b in 80j at a, so for all nodes adjacent to a, aka all nodes where there's a dislike relationship, we say if a is in first, in fifth, if a is in first, then if b is in first, we immediately return 0. We return false. Or else, we don't need the else here because it's after return statement. If b is in second, then continue. This is sort of like a scene set in an ordinary breadth first search so that we don't have to iterate through the same thing a million times. Otherwise, second dot add b. So we really just have to say if b not in second, second dot add b, and then q dot append left b. And then we just say the same thing, but if a is in second. So we'll say else if b in second, return 0. If b not in first, first dot add b, q dot append left b. And then if it ever makes it through this entire breadth first search, then we can return 1. So when we run this, it will work for all of our test cases. However, if we said, for example, n equals 6, and then right here we had another edge, we had another dislike where we said 5 and 6 don't get along. And we, it's difficult to write out the test case, but what I'm going for is if the mapping here is a disconnected graph, if there's multiple components. So if we said, great, there's this whole thing, this works, that checks out, while q, whatever, we start from the first node and we build out. But then if there's a whole other separate component, let's say 5, 6, n is 10, and then nodes 5 through 10 don't work. The problem is this is only accessing that component that includes the first node. So we need to actually go through and make sure that we put every single node in either first or second, regardless of if there's any way to reach it through the dislikes, regardless of if it's included in this graph, the same component of the graph that node 1 is in. So the way that we would do that is we would say for I in range 1 n plus 1, because it's 1 indexed. Then we have all this indented. And we say, we actually, interestingly, don't even have to have, well, no, we do. We have to say q dot append I, and then we don't need this. Oops, we still need to make the q. Cool. This works because n has 10 nodes, and this is just this is saying, okay, all of the nodes past 4 are just freestanding nodes. They actually don't matter anymore at all. The final thing to point out that's interesting is we don't actually put anything in first or second to start. So for example, when we start and we say I is 1, append 1 to q, my computer froze. While q, a is q dot pop, nothing's actually in first or second. But because we didn't say else if a in second, it means that the first node we look at in the breadth first search here will not be put into any set until the second node is, and then looks at the first node again, which to me is kind of elegant and cool. So there it is. It seems like it's a pretty random time complexity. I think that I can't really see doing this in any quicker or slower way. Looking through, it looks like maybe they cover some common corner cases, but it looks like about the same. I think maybe they use an actual level order here. Instead of using two sets, they use one set, which maybe is what's giving them the edge. But that's the daily problem. It's another pretty approachable graph problem, which is cool to see.